with you.
Cool. Okay, well, yeah, thanks, Vincent. Thanks a lot for the introduction and also for organizing this. I think it's a really cool initiative. Yeah, as Vincent said, I will be talking a bit about lead-tin and mainly about mobile ions today. Originally, I wanted to present something else, but because it was a bit short notice, I did not have time to prepare that fully. But at the end of my presentation, I will still tell you a bit about all perovskite tandem solar cells, because I just want to show you something that we've recently been working on also. All right, but we'll start with the current losses in perovskite. And before we start off, I just want to give you a bit of an idea of the motivation behind this project. So I work on lead-tin perovskite normally. And actually, these lead-tin perovskites generally suffer from quite large current losses, often a bit more than their purely lead-based counterparts, although recently there have been some really nice advancements. But because these lead-tin perovskites suffer from such large current losses, the idea was to sort of look into these current losses a bit more. And first of all, figure out to what extent these current losses are optical losses, or to what extent they come from recombination losses. And then afterwards, we wanted to also understand these recombination losses a bit better, so figure out where they come from. And in particular, we wanted to look at whether they might be due to doping, because lead-tin perovskites are a bit notorious because the tin 2+ in a material can easily oxidize to tin 4+. And this can then lead to defects, but it can also dope the material. So we wanted to see if this doping somehow has an effect on the current losses, or if there might be other mechanisms at play. So for example, mobile ions. Now, to just quickly give you an idea of the system that we worked with, we had a 50-50 lead-tin perovskite solar cell. The best devices had a PCE of about 17.5%. On average, it was more like 16.8 or so. All right, so that is the system that we worked with. Now, the first thing we did was look at the internal and the external quantum efficiency, because looking at this, we can actually get an idea about the different losses, and most importantly, figure out to what extent we have optical losses and what are recombination losses. Now, as you can see here, we actually have very strong optical losses, almost 7 milliamps per centimeter square. And that is mainly due to the perovskite not being thick enough. So our layers here are about 400 nanometers thick, which is by far not thick enough to absorb all the light. It's a bit tricky to make thicker perovskite solar cells. So that is why here we had a thin cell. So we had quite strong optical losses. But as you can see, actually on top of that, we also had quite significant collection losses, about 2 milliamps per centimeter square. And it's these collection losses that we wanted to look into a bit further. So we wanted to understand where they come from. And we did have a hypothesis about this. And the hypothesis had to do with field screening. Now, basically, when you switch your device, like the bias from VOC to 0 volts, normally you should get nice and steep bends. And at this point, you should be efficiently extracting all your charges, right? But what we think might actually be happening is that when we switch to 0 volts, initially we have nice and steep bends and we're extracting all our charges. But then charged species, so either ions or doping-induced species, they might redistribute in our cell and they might move to the interface of the perovskite with the transport layers. And there they could then start to screen the field. And this field screening could cause the nice and steep bends that we had at the start to sort of flatten out and thereby reduce our charge extraction efficiency. Now, in order to figure out if we indeed suffer from such a change in charge extraction efficiency over time, we perform some photoluminescence measurements where we change the bias of the device. So this is depicted here on the right. So we start with the device bias at VOC, and we continuously take PL spectra. And then at T0, we switch the device bias to 0 volts. So we switch to short circuit conditions. Now, normally, if you take a PL spectrum at short circuit conditions, you would expect the PL to be completely or almost completely quenched, because you should be efficiently extracting all your charges. And therefore, there shouldn't really be anything left in the device to recombine, and therefore no PL. But what we found actually was that when we switch to 0 volts, initially the PL almost completely quenches, But then over the course of a few seconds, it sort of slowly creeps back up again before eventually stabilizing. And you can see that nicely here on the right. So at t0, the PL is almost completely gone, and then it comes back up over the course of 2-3 seconds before eventually stabilizing. And that is actually very interesting, because that means that even though we're initially very efficiently taking all our charges out, something happens that makes us lose this efficiency. And actually, if we look at the current that we're extracting simultaneously, we see the effects of this reduction in extraction efficiency. Because when we switch to JSC, initially we have a high current density, but then over the course of the first 2-3 seconds, we lose quite a bit of current before it eventually stabilizes. And for the lead-tin perovskites, we actually lose on average about 1.4 milliamps per centimeter square. So that is actually quite a significant loss. All right, so we know that something is happening that causes a reduction in the charge extraction efficiency. Now the question is, what is going on there then exactly? So is this caused by doping somehow, or is it due to mobile ions? And actually, in order to distinguish between these two, we performed a bunch of transient measurements. And these measurements were actually performed by Vincent. First, we performed base measurements, which stands for bias-assisted charge extraction. And what we do there is actually, we have our device in the dark, and we first bias it at VOC, and then we switch to 0 volts. And we just measure the current that comes out after we switch to 0 volts. And the results are displayed here on the left. And what you can actually see is that as soon as we go to 0 volts, we have some extraction, some current coming out at very fast time scales, so at 10 to the -7. And this is actually our so-called CU charge. So our device works as a sort of capacitance. And so there's a certain charge on the plates that we're extracting initially, and that is called the CU charge. And those are just electrons. So we see that the electrons are actually moving very fast at about 10 to the -7, 10 to the -6 seconds. But then as we start looking at the slower time scales, at some point we see another rise, an additional rise. And this is actually caused by the mobile ions. So this is at much slower time scales. Those ions are moving around. And what you see here, I mean, of course, we're not actually extracting the ions into our electrical circuit, but we see a compensation current for these ions. And what's interesting is actually, all right, these ions move at much slower time scales, but if we look a bit further, they actually move at exactly the same time scales on which our current losses take place. Now, to confirm this further, we also performed what we call fast JV measurements, where basically we just measure JVs at different scan speeds. And what we find here is that when we are at like high scan speeds, so over here, at the high scan speeds, we have a high JSC. And as we start scanning slower and slower, at some point we have a sudden drop in JSC. And again, this is exactly at the time scale at which the ions are moving. So that just means that now that we start scanning slower, the ions have enough time to move to the sides and start screening the field. All right, so evidence is sort of stacking up against these ions here for being the cause of our current losses. Now, there was one more measurement that we wanted to perform, and this was a SALIF measurement, which stands for charge extraction by a linearly increasing voltage. And this is actually a very powerful measurement, and I will try to explain why that is the case. So first, what is the measurement? Well, as the name says, we linearly increase the voltage. So we have our device, normally in the dark again. We start at 0 volts, and then we linearly increase our voltage to a certain maximum voltage. Now, often we went to about 400 millivolts, but this, I mean, in principle, you can change. And as we increase our voltage, we are extracting charge. Now, the interesting thing about this measurement is that normally you always extract your CU charge. So again, the device works as a sort of capacitance, so there is some charge present in the system, and this we initially extract. And this normally would sort of look like this, like a square. In reality, it's not completely square because of the response time of the system, but yeah, generally you have your CU charge, that you can extract with this Salif measurement. But the interesting thing is that if there are other charges present in the system, you can also see them in the Salif measurement, but only if they are at significant concentrations compared to the Cu charge. So that means that if you have a significant concentration of doping, then you see an additional bump on top of this, on top of the Cu charge. And same for the ions, but then of course at much slower timescales. But if we have a significant concentration of mobile ions in the system that are moving around, then we would again get a bump on top of the Cu charge. And that is what makes this technique so powerful, because basically, if you see the charge in the Salif measurement, then it's sort of relevant for the device performance. Whereas if you don't see it, that means that the concentration is below the Cu charge. And we've done some simulations that show that then it's likely not relevant for the device performance. All right, so that is how Salif measurements work. If you want to read more, I would recommend these two references, one about Salif in general and one about how Salif can be used to quantify doping. All right, so that's how it works. Now we performed these measurements and you can see the results over here. And as you can see, well, like we already expected, we have a strong ionic charge at the slow timescales that is on top of the Cu charge. But if we look at the shorter timescales, we do not see any bump that would indicate that doping is there in significant concentrations. So once again, it seems like mobile ions are affecting our device, but there does not seem to be any doping. Now, finally, as a sort of sanity check, we also performed some photo-Salif measurements. And that is basically the same as the normal Salif measurement, except that here at the start of our linearly increasing voltage, we add a laser pulse. And the reason we did this measurement was actually to sort of visualize what certain doping concentrations would look like had they been there. So we just wanted to prove that indeed, if there are a certain amount of charges in the system, you do see them and they make this sort of bump. So we had our laser pulse and we pulsed with different intensities to generate a known charge carrier concentration. And then we looked at what the Salif response looked like. And indeed, you see that as we increase the laser intensity, so we generate more carriers in the system, we get this bump. But when we don't use the laser, there's really no bump. So that really is once again a confirmation that we don't have a significant amount of doping in the system. At least the doping should not be affecting the device performance or causing these transient current losses. All right, so basically now for these lead-tin perovskite starter cells, we figured out that mobile ions are causing transient current losses and the doping is probably not causing any of these transient losses. Now, of course, there is one important question remaining, and that will be, well, okay, this is for lead-tin, but what about purely lead-based perovskites? Is this loss mechanism that we've observed, is this inherent to lead-tin perovskites, or is it actually just a general loss mechanism for perovskite? So in order to figure this out, we performed the same measurements, but then on purely lead-based perovskites. These cells were actually made by Pacho for all the PIN cells and by Max and Emilio for the NIP cells. Yeah, and like I said, we performed the same measurements. And actually, well, we also got the same results. So for all of these different compositions that we looked into, for all of them, we did observe a current decay over the first few seconds. And also for all of them, this was accompanied by an increase in PL over the first few seconds after switching to 0 volts. Now, once again, we also performed these fast JV measurements. This was again done by Vincent. And like I've showed you before, basically when we scan fast, we have a higher current. And as we start scanning slower and slower, at some point the current drops because the ions are able to follow the field again. And then if we scan even slower, it stabilizes because, yeah, the ions, well, if we scan even slower, the ions have even more time. So they just fully screen the field, basically. All right. So from that, we concluded that, well, in the lead-tin perovskites, mobile ions rather than doping cause band flattening, and this band flattening in change leads to a reduced charge extraction efficiency, and this then causes quite significant current losses. And we then were also able to sort of generalize this, and we observed the same loss mechanisms in a range of pure lead-based perovskite solar cells. So that's an interesting conclusion, but it actually also opens up a whole range of questions. First, maybe most importantly, can we mitigate this effect? Because of course, we want to make our solar cells as efficient as possible, right? So we have to get rid of this loss mechanism somehow. So is there a way that we can either reduce the impact that the mobile ions have on these current losses, maybe by changing transport layers or by using additives? Or can we maybe just get rid of the mobile ions altogether? Can we just make sure that they don't move around in the system anymore? And there, for example, we could look at different compositions. And then sort of related to that, well, what about the record efficiency cells? Because the record efficiency cells currently, they are really moving towards the theoretical limits, well, theoretical current limits. So what about those? Do they still suffer from current losses? Or, and that would actually be very interesting, maybe they don't. And if they don't, well, why not? Have they already found somehow a way to mitigate this? So that would actually, I mean, we could learn really a lot from this, and hopefully we will be measuring some of these record efficiency cells soon to figure out more. Well, then other questions like, what are the effects of aging? We know that in general, the concentration of mobile ions increases a bit. So what exactly is going on there? Or maybe we can also look beyond perovskites and look at other emerging materials for PV. So is this current decay, well, or mobile ions in general, is this an effect that is just limited to perovskite, or do we also see it in other systems? And then finally, one more question that sort of comes up. Well, what will be the implication for perovskite-based tandems? And most importantly, what will be the implications for all perovskite tandems? Because if you have two subcells and both of them have these current losses, do we then see this effect extra strong in these tandems?